So when you look at this question, you see that you have e squared and a plus sign. And so that looks very, very similar to the arctangent formula. So you're kind of thinking to yourself that maybe this integrand would fit tan inverse. However, what most people would probably do when they look at this is they wouldn't think about that unless they were like in this particular section. Most students and just people in general would probably think, okay, well, let me try u substitution. And they might pick u to be equal to the e to the 2t. But then when they take the du, the derivative, they're going to have e to the 2t times 2 dt. And you'll notice that there's no way that you're going to somehow get this e to the t to become an e to the 2t. And so for that reason, u substitution does not work, and you have to kind of think about this arctan as the integration formula that might fit the bill for this integral. So our arctan formula, again, is our du over a squared plus u squared is equal to 1 over a tan inverse u over a plus c. So to try to see if this integral fits that, what we would say to ourselves is we would say, okay, we have e to the t over 1 plus e to the 2t dt. And we would say that this a would be equal to 1. And then our u would be equal to e to the t. And you'll see that because if you look at this e to the 2t, that is the same thing as e to the t quantity squared. So our u is actually e to the t. And then our du would just be e to the t dt. So this is kind of our key for using this arctan formula. Now, in terms of the current integral, we have everything we're set because our du is in the numerator. So we really can go straight to just plug it into the formula. So we would have 1 over a, which is 1, tan inverse u, e to the t, over our a, which is 1, plus c. And then, of course, all of these 1's can be dropped. So you just have tan inverse e to the t plus c as your final answer.